Hello, students. Getting into the MCs for 13.3, and there's not a ton of them. 11, 13, 14, and 16, 17, 18. So not a ton. Let's take a look at them. All right. Question 11. Find the distance between the centers of the two circles with these equations. In this case, obviously, if you take a moment and you just say, hold on, let me find the center of this one. Let me find the center of the other one. There are just two circles. Just find the centers. And the center will be a point. So it'll be like an AB. And this one over here, it will be a point 2. We'll call it CD. And then just ask yourself, how far over, how far up, and then use the Pythagorean theorem to find that distance. Okay. Great question there. 11. What was it? 13 to 14. Okay, so 13 to 14. So here, ABC is a right triangle with a right angle at C. CD is the altitude to the hypotenuse, which does divide the triangle into two right triangles marked 1 and 2. Okay, they're listed right here, so we can see it. Prove the following. The area of 1 compared to the area of the whole is B squared to C squared. Okay. Prove the area of 2 is A squared to C squared. Okay. And use these parts to show that area 1 plus area 2 divided by the whole area is A squared plus B squared, the whole thing divided by C squared. And use that part and the fact that area 1 plus area 2 equals area 3 to prove the Pythagorean theorem. And so if you get to the end, you get A squared plus B squared divided by C squared. But you know that these are equal. This ratio has to equal the number 1. So that's what you're going to kind of use here if you needed a little hint. This has to equal 1. And from there, you should be able to show that A squared plus B squared is equal to C squared. Okay. It does use the fact that we have similar triangles. Big hint, we have similar triangles. So the ratio of the sides is going to be squared when we get to area. So this is actually pretty cool. And number 14. Draw several kinds of triangles, including a right triangle. Draw a square on each side. Compute the areas of the squares and use this information to investigate whether the Pythagorean theorem works only for right triangles. Use a geometric utility if available. Big hint, you have a geometric utility available. And the only thing that you have to do here is, let's clear it all. Let's clear it all and just kind of show what am I talking about. Just make a triangle. Any triangle at all. Make squares on the sides. Just use the regular polygon option here. Okay. I'm serious. It's just quicker. And so I'll make these on the sides. All right. Compute the areas. And then what else do I want to do? Then, ooh, I need to measure the angle here. I need to measure this angle. There we go. There we go. And lastly, this angle over here. And that way I can kind of see if I do hit a right angle at any one of those. Okay. So, oh, and let me go over to the little algebra tool as well, because I don't want to do this all by my lonesome. Let's see, I have poly 1, poly 2, and poly 3. So let's do this. Let's make sure that we always have poly 1 plus poly 3. Okay. And so right now, poly 1 plus poly 3 is 95. So notice the area of the two squares here is, when I add them together, is bigger than the third square. And if you look at the type of triangle that we have an acute triangle. All the angles are less than 90 degrees. Okay. So now here we go. Let's click and kind of move some of these around again. Let's see if I can make this one a 90-degree angle or close to it. It's so close to 90. And 98 point. Okay, so if it was 90 degrees, then the sum of the small ones would be equal to the big one. But now watch this. Let me push B in to make this an obtuse triangle, right? Now, if I add these two together, it's actually less than the area of the big one. So a squared plus b squared is less than c squared, and that's when it's obtuse. And this does lead to like a really handy idea. If you have a squared plus b squared and it equals c squared, then you know that you have a right triangle. If you have a squared plus b squared and the small ones, when you add up those areas, if they can't even get to the big one, which means it's less than c squared, it means this area over here is bigger, and that's because the angle is bigger. So that is obtuse. And likewise, when we had a squared plus b squared and it was bigger than c squared was smaller. This one was smaller because the angle was smaller than a right angle, and therefore this would be an acute triangle. So if the three sides make a triangle using the triangle inequality, you can use something like this with the Pythagorean theorem to be able to tell you what type of a triangle it is without having to build it and everything like that. Just a squared plus b squared, compare it to c squared. It's either equal, greater, or less than. That's it. So to me, that's like super cool and extremely handy. So I don't have to try to sketch it out. I can just use that to get to my end result. And lastly, 16 through 18, so questions from the classroom. Part of the discussion, students were asked about each side. A student said, if a similar polygon was constructed, will the same relationship hold? Again, if you've been watching the videos, you should be able to answer this one. If not, I recommend the videos, but test it out if you need to on GeoGebra. We just built one with squares. You could build one with triangles. You could build one with, and it says similar polygons. So triangles, you could build pentagons, hexagons. You could build whatever you want. 17, Bella says the equation of the circle she just drew is this equals, equals negative 16. How do you respond to what she just did? You tell me if that makes sense. Remember, the equation would equal r squared. Can r squared equal negative 16? All right. And lastly, one leg of a right triangle is 3. The hypotenuse is 5. She was finding the length by doing the square root of 3 squared plus 5 squared. Very common. This is very common among students as they try these things out, is they do what you do. And if you did 3 squared plus 4 squared, and then you took the square root at some point in time, again, to get like a 3, 4 triangle, and you find the other side is 5, notice you are taking the two legs and putting them in here. So oftentimes, if you were missing one of the legs, the student would do the same thing because they're not catching on. They're not seeing why you used those. So it's very important that you put down all of your steps as you go through the problems, especially when you're dealing with students seeing it for the first time. Okay, so let's see here. I think that's 16 through 18, and I believe that's it. I do want to bring up one other question. I did not put this in the homework intentionally because I think it can be a little bit intimidating. But right here in question 5 is what is something that I think will be very helpful for some of you. If you've ever wanted to be able to create triangles that are right triangles, but the side lengths are all like integers or whole number values, they don't have square roots, this is the technique to use. So you can always scale it up. So for example, we've been doing 3, 4, 5 triangles now. So you can certainly do a 3, 4, 5, and you can just scale it up, which means a 6, 8, 10 would also work, which means, go up even further, a 9, 12, 15, just multiply all by 3. So if you use kind of floffing techniques, you can keep going up, but you could actually create other ones too. And so now this technique down here in part D tells you how to do that. And so I wanted to show it to you, but I didn't want to assign it. So, I mean, I guess forgive me for not assigning it or appreciate it. I'm not sure which one you're at. But notice here, A is equal to 2uv, B is equal to u squared minus v squared, and C is u squared plus v squared. Okay, where u and v are natural numbers with u greater than v. All right, well, let's I don't know. Should we try something here? Let's try U is 4 and V, again, U has to be bigger than V, so I don't know, 3? Okay, so there we go. Okay, so U is 4, V is 3. So let's see here. So A is 2 times U times V. So U times V is 12, so that's 24. U squared is 16 minus V squared, which is 9, so that becomes 7. And U squared is 16 and V squared is 9, and that becomes 25. What it's telling you is you can create this triangle right here is a 7, 24, 25 triangle. Now you can check it with the triangle inequality. It holds. It actually creates a triangle. But guess what else is cool? 7 squared plus 24 squared. Guess what it equals? It equals 25 squared. This right here is a right triangle. And we just built it. We created a new right triangle with whole number sides by just plugging in some U's and V values. And it just kind of, this process creates Pythagorean triples. Okay. That, to me, is pretty cool. So let's look, maybe we'll do one more, right? Just because you're like, okay, that was kind of a fluke. Okay, well, let's do U equals 5 and V equals 2. Okay, so we go up here. So U times V times 2. So this is 10 times 2. Okay, so A is now 20. And then I do 25. So B is 25 minus 4, which is 21. And C is 25 plus 4, which is 29. Okay, so theoretically, okay, maybe not. Maybe I screwed this up. Theoretically, a 20, 21, 29 triangle can be built. And let's check ourselves here. So I need 20, 21, and 29. And we're going to test to see if this is a Pythagorean theorem. I'm going to grab Desmos real quick. I guess I could just use the GeoGebra calculator here. Okay, let me get rid of some of what I've written up here just so it doesn't get too messy when I go to GeoGebra. But let's try it. Let's jump over to GeoGebra and do a little bit of calculation. Algebra. Boop. Okay, so here we go. Let's type it in. I need 20 squared, right? Plus 21 squared. Okay, and I need now 29 squared, and it's 841. There's another right triangle that you can use with nice numbers, a 20, a 21, and a 29, and that's how you can create them. So again, if you were interested at all in kind of how do you keep coming up with those numbers, there is a process. There is a mathematical approach that we use. It's not that we just guess and keep guessing until we get one that works. We use something like this, which is a way to create Pythagorean triples. All right. Question 7 is also super cool, but we'll have to save that one for another time. All right. Thanks so much. If you have questions, please let me know. Email. I can make another video for you. I can jump into Zoom with you. I can meet you on campus. I can stay before or after class. Just let me know how I can support you. All right. Off you go.